Hey everyone, this is Tom Salemi of Device Talks. We missed you so much. Welcome back to Device Talks Tuesdays. It's been a couple of weeks. Happy to start our summer season with our very good friends from Aptyx, who are putting on this discussion, this presentation, what every engineer should know to prevent warp. We've got a very full, robust, and insightful presentation for you that you'll be able to access in the resource widget. So please make sure you walk away with that after you're done watching our experts go through it. We'll be taking questions. We'll be collecting questions throughout. We may have a few that we'll bring in during the presentation. Likely we'll get to most audience questions at the end. But as always, please don't wait until the end to ask your questions. Get them in early. That way you'll have a better shot of getting them answered. And you'll also just give us a sense as to how many questions we'll be managing. So it makes the whole thing a bit easier. As always, any questions that are asked but aren't addressed during the presentation, they'll be addressed after we run out of time. Aptyx will have all the questions and can get answers back to you as well. If you're watching us on demand, thank you very much for tuning in, and you're also welcome to ask questions as well. That way, again, Aptyx will have access to the Q&A box, and you'll have a reply. Don't feel left out. Please ask questions at any time. Actually, if you're watching this on demand, it's at your convenience. Do it whenever you want. Beginning, end, it's all the same. It's all going to go to Aptyx. With that, we'll get into just a little bit about us. Device Talks. We have podcasts, lots of podcasts, more coming at devicetalks.com or any major podcast player. Aptyx is a frequent sponsor of our podcast. We're very grateful for that, including our MedTech Women Talks podcast. So great to continue to work with these fine folks. And I don't have a slide for our Device Talks events because we're in between events, but we just had a very successful Device Talks Boston, and work is underway on Device Talks West, and that'll take place October 16th and 17th. Go to devicetalks.com for more information about that. All right, let's get into our discussion.
In the bustling city of MedTechtropolis, where speed, quality, and life-saving innovation reigns, an Aptyx engineer named Ray Scherer discovered his extraordinary gift for predictive engineering. With an uncanny ability to foresee and course-correct using design for manufacturing, giving him an ability to dodge delays and evade catastrophic costs, he became known as the Great Raydini. As medical device and manufacturers faced surging demand for their groundbreaking products, a sinister force loomed on the horizon. Warp, a rogue villain with the power to manipulate time and space itself, emerged from the shadows. Driven by a thirst for chaos and destruction, Warp sought to disrupt manufacturing operations and plunge profits into darkness. The Great Raydini, armed with predictive prowess, rallied the Aptyx engineering team to defend against Warp's temporal terrors. With the fabric of reality bending to Warp's will, they faced a relentless onslaught of twisted challenges and warped components. Determined to save their city from destruction, the Great Raydini, his team, and fellow Avenger Brian Pelley pushed themselves to the limits, using their ingenuity, resourcefulness, and combined mastery of Moldflow to outsmart Warp at every turn. After a grueling battle, the Great Raydini, Brian, and their team emerged victorious, banishing Warp back to the depths of the time-space continuum. With MedTechtropolis safe once more, the Great Raydini's legend grew even stronger, inspiring engineers everywhere to harness the power of technology for good.
That's great. Future
fun,
Device
right?
Talks Tuesdays webinar sponsors, be on note that I demand a funny video at the start of every presentation from here on in, because it's a great way to start with some laughter and chuckles. So great job.
Isn't it? Thanks.
Yeah.
Ray and Brian may not be actual superheroes, but they really have saved the day more times than we can count. And Ray's nickname around Aptyx is, in fact, the Raydini. And as you and the audience probably know, plastic is the leading material in medical devices, medical device components. And it is not unheard of for a single component to cause issues, to cause a line down, to upset a multi-million-dollar project, to cause delays in care to patients. And of course, none of us want that. So we are extremely happy to have these superheroes on our team. And I'll turn it back to them briefly. First, I'm going to cover what we're going to talk about today. So I'll do a very short Aptyx overview. Brian will tell us a little bit about Autodesk and then cover successful design principles. Ray's going to hit theory and concepts for warpage, but much more interesting than even that, he's going to show you some of that in real life with some great applications, and then Q&A. So Aptyx brings together the aptitude and excellence of more than a dozen companies with a 70-year track record in manufacturing. And we absolutely love solving complex challenges. It's just part of our DNA. And if you're thinking, I don't know the name, and as a marketing person here, I'm hoping quite a few of you do know the name now, but I'm quite sure many of the legacy company names that you see on the bottom of the slide that today make up Aptyx. And as a fully integrated company, we have more than 10 locations globally, and we've combined deep expertise and specialized capabilities to be a single resource for life science partners. And that includes extrusion, molding, and not just injection molding that we'll talk about today, but also dip molding, where we're a global leader, and blow molding, coating solutions. We do have a webinar on that, by the way. We cover from application to automation and coding. We do assembly from subassembly to finished devices, and also have tooling in-house. And then taking a look at molding, our sweet spot is really complex processes. So insert molding, two-shot molding, over molding, even in-mold decorating. You can see big range of press sizes from 5 to 940, covering hundreds of materials, specializing in high temp and highly engineered. I use advanced technologies such as Kistler, and then really why we are here today. Best-in-class DFM support with predictive engineering and Moldflow, all focus on helping our customers get to market faster, more efficiently, so that we can all get better care to patients and care teams globally. And with that, I'm going to turn it over to Brian.
Wow, thanks. I hope we can live up to that intro. So Brian Pelley, Solutions Engineer with Autodesk, and I grew up in Boston. I went to school at UMass Lowell, and my career is all over the map. But my one true superpower was how I apply Moldflow, and I feel very fortunate for that. I joined HP, and that's what brought me up to Oregon in 2000. I joined Moldflow in 2005, and then Autodesk acquired Moldflow around 2009. And somewhere in between there is where I met Ray. The rest is history. I'm that guy that, even as a kid, would want to take things apart just to see how they're made. And more importantly, not just why they're made, but why they break as well. So I was just destined to be an engineer. Autodesk and Moldflow, by the name, you may not be familiar or may not be intuitive. We do get calls for this hybrid desk, this mythical hybrid desk. And every so often, and these are real calls, we get folks asking for help removing mold from bathrooms. So we're not making that up, but Autodesk has industry platforms, technologies that you are using most likely that focus on helping you design and make things. So part of that technology collection is simulation, and it's very important, especially in the design phase, because what you're designing in CAD is not going to be what you get. Even prototypes are misleading at times, and we react differently to feedback. Instant feedback is when we react and we learn. The long-term feedback is something we procrastinate on doing something about, and that is why we need a tool, a predictive engineering tool like Moldflow, to help us see those potential issues that are going to happen downstream and make better decisions sooner. Our villain for the day, there are many. Sometimes it's which is the least of all these evils, but today we're going to focus on warpage And this is a sustainability slide that I got lazy, didn't change much, but it really hits the point of why we need to start early. Any sustainability initiative or cost initiative, it's all embodied in the initial design stages. If you don't see that up front early, it trickles downstream and it's more difficult to combat. In some cases, you can't. So if you look at the principles of what makes a successful plastic design phase, there are many aspects to it. And it may seem a little daunting and a lot to understand. And in some cases, you may not have this knowledge and need to leverage folks like Ray and get them involved early. But the good news is there's just three main variables that designers can focus on: geometry, material, and gate location, to use Moldflow with. And over 80% of root causes of issues that I see are pertain to these three variables. So there's the good news. Material, for in this case, we're talking warpage, is very important to understand the behavior of crystalline materials. They shrink a lot more. They shrink different in flow and cross-flow directions, so they're a more difficult beast to tame. Amorphous materials are a little more isotropic and less shrinkage, a little easier to deal with. And when you get into fiber-filled materials, it's a lot more complex. We can handle it, but you got to use a different tool set, engineering approach than what we're going to show today. So geometry, thickness drives flow and shrinkage, variation in shrinkage. Our shape matters as far as rims and gussets and ribs, add stiffness to the geometry. And again, thickness will tend to influence, in this case, shrinkage and warpage. Gate location is very important too. Where we gate it, you can think of that as the heart and pumping pressure to your extremities. And the farther away, we have less dimensional control. And we have these shape factors also that are influenced by where we gate it, center versus. And if we want to control region to region and we add more gates, we add another villain, and that's weld lines for every gate we add. Here's a snapshot within Moldflow just to give you a reference of materials: polypropylene, crystalline material on the left, ABS, amorphous on the right, and center gate on the top and an end gate on the bottom. So we can see just between material and gate location that the overall magnitude of warp is going to change quite a bit sometimes, and Ray will get into the details of geometry. So if everything was perfect, or lived in an ideal fairyland somewhere, all our parts would shrink uniformly in each direction, and we just make our molds bigger and story's over. But that doesn't happen. So there's a lot of regional shrinkage, even through thickness, even across the thickness. And so these definitely have shape factors. And here I'm going to tie back my schooling. I originally started as a civil engineer before I switched over to plastics. So I learned these shape properties and how they can influence stiffness and calculating mass, center of mass, and a moment of inertia, and this neutral axis. So if you apply a load to this shape, it's going to bend and the stresses are going to balance along this theoretical axis. And in this case, the load is shrinkage. And so if you're thick and you shrink more than thin on the bottom, you're going to create this kind of pinch on the top. And it's going to shrink less on the bottom, and so you'll get this shape factor. There are many different aspects to shrinkage. We're going to focus on differential with a couple of little cooling influences that Ray will talk to. It's a lot more in-depth as far as different aspects around what causes warpage, and I've got some background information here in these QR codes and links. So with that, I'll pass it over to you, Ray.
Hi, my name is Ray Scherer, Global Engineering Manager at Aptyx. And before I get started, I needed to express a disclaimer here that I take no responsibility for what people call me. My background is really as a tooling engineer. I got started as a mold designer way back in the day of drafting boards. By the mid-90s, I was responsible for getting tools built and getting them into production. And I didn't really know a whole lot, didn't have a whole lot of predictive tools. Through that stretch, I realized one thing, and that was after I built the mold, I didn't like the surprises that came at T1. I'd take my first shots and suddenly I'd have a warped part, for instance. Could be something else, but I look at that part and it surprised me, right? And what I learned about myself at that point in time was I'm pretty pretty clear. I became motivated by what I don't like. Now, maybe not everybody's that way, but that was me. I did not like being that guy at the end of a tool build with a surprise. So I found myself at the time really leaning on luck. That didn't make me happy. I also found myself leaning on chance. That wasn't good either. All that added up to delays. I didn't like that either. And of course, I didn't like plastic potato chips. I really only liked the edible kind. So that launched me off, in search. I wanted to get back certainty. I wanted to get predictability, and I want to get punctuality. And then I only wanted to eat the edible kind. So about early 2000s, that's what Brian mentioned, it was a life change for me. At that point in time, I bumped into Moldflow. I got a seat of it, met Brian Pelley, and I had no idea what was going to happen in front of me, but I figured, hey, I'll just use this tool as a tool in my toolbox. I started using it, and I started learning more and more, and some of the lessons learned over a long period of time I want to share with you today. So as Brian mentioned, we won't address every pitfall in plastics. We're just going to focus on warp today, but we'll focus on some warp principles and techniques that you guys can employ. And they're guaranteed to be a game changer for you as a designer. So if you're a designer on this call, focus in. You'll learn some things that you may or may not know already, but if you don't know them, they'll definitely be a game changer in how you think about developing your design. What you will learn. As Brian mentioned, we'll focus on how part design geometry drives warp and why. Just a little side note here, these techniques that we're talking about will work on unfilled resins, work on semi-crystalline, amorphous. What they won't work on very well is filled resins. So we do a lot of filled resins at Aptyx, fiber filled, and they're a beast of their own. But this presentation will focus mainly on the unfilled resins. How can you use that knowledge to imprison the warp bilum forever? That's what we hope you get out of this today, is to be able to take this, and then when you look at your part, I believe you'll be able to look at your part and predict how it's going to warp before you even get it molded. And with that knowledge, there's certain techniques you can put in place to help prevent that or steer it. First up, I want to get into a question. What is volumetric shrinkage? Now, that is a result that's in Moldflow. If you go away and don't remember anything today but one thing, this is the piece you want to remember. The polymer, when it's heated, expands. That's what's represented by this white box. When it cools, it contracts, and that's by the solidified volume box. So if you think about it a minute, what Moldflow shows is the percentage change. So basically, it's going to take that 100% volume, and it's going to give you a value and say, how much did we change percentage? Now, this is different than linear shrink. It's related, though. As we build molds, we use a linear shrink rate, and that just scales the part uniformly. But the reality of it is the part doesn't shrink uniformly. We'll get into that more. So that distance, that delta can be affected. If you're in a crystalline resin, for instance, that white delta there will be larger if you're in an amorphous resin. So this is really key, but I want to point out a couple of things here before we go on. Not only does the volume decrease, but so does the length. So if you start with this box right here and just look at it, the white length is how we started in the mold. When we came out, it turned into this bluish, purplish length. And therein lies the problem, is the lengths. So if you get varying lengths happening in your part when it shrinks, it's going to warp. And that's really what the focal point is today. So the question becomes, what causes volumetric shrink to vary? We'll put a little simple plate up here with a gate in the middle. And I have a legend out here. This is the volumetric shrinkage legend. It shows it goes from about 1.4% to about 4.2%. This was a little polycarb plate that I modeled up. And so what happens is, first off, as you guys know, shrink increases as thickness increases. That's pretty well known by everybody. If you got a super thick part, it's going to shrink more than a thin part. Another reason parts shrink is due to the distance from the gate. So if you look on this image right here, I got some, so I can put some pointers here. There we go. So we got some readouts of some nodes on this part where the volumetric shrink is recorded. So if you notice, as you get away from that gate, further and further, that volumetric shrink value goes up and up. It starts at 2.5, ends at 4. Pretty significant. So gate location is extremely important. But what I want to point out is the piece of information that I never really understood. And when I did, it started to change things for me, and that is edges. There's an edge effect that's way different than the center of the part. You can see that here. You can see that the edge is shrinking at about 1.4%, and as you go down that edge, you get as high as 2.6. But it's significantly different than the center. And the way that Moldflow works is everything is blue. In the bluish range is going to be your lower shrinkage, and therefore when it comes out of the mold, it's going to be longer. Anything in the hotter ranges is going to shrink more and be shorter. And one of the oddities in this whole thing sometimes is this center region that also is red, you might notice. Brian, you want to comment on that one? I think you got some good information there.
Yeah, we had a question from the audience about that as well.
Yeah, it sticks out. Yeah, it sticks out. Gate does influence things, and in this case, when you run through a thin or small area, you do generate shear heating, and so that can cause a spike in temperature, and so we're seeing an effect of shear heating. The other component that may happen here is if you stop packing out the part before that area freezes, we can also see higher volumetric shrinkage around the gate area. So the ring around the gate is sometimes normal, but can be dealt with as far as processing variation. Anything else, Ray, on that?
No, that's good. Thanks, Brian. That one, let's see. All right. Another concept for you guys to think about is this neutral axis. Brian referred to it. And I got a little handle over here. We'll come back to this handle later in the presentation. But if you just envision sort of a neutral axis running through the center of this part, what happens is if we have an imbalance of volumetric shrink on both sides of that axis, something's going to happen. So we just spoke a few moments ago about the edge effects around a part. They go longer and the middle it shrinks more. And becomes shorter. So that forces a bend. So if you have some symmetry about that point, you stay flat. If you have asymmetry around that neutral axis, your part will warp. And that's a fundamental piece that will carry into the presentation here as we go forward. So just those two pieces, if you hang on to those, the volumetric shrink concept and the neutral axis, it'll all make sense to you. All right. So question is how does volumetric shrink promote warp? We've touched on that on the edge, but here's a little plate just to illustrate it. If you take a look at the top view, it's a little 3D view. It's that simple plate that we had with a couple of ribs, about 1/8 of an inch tall, not much. But if you look at the blue pattern, you'll see there's a lot of blue coming off of those edges. That means that length right there is not going to shrink as much as the middle of the part, which is in the 3% range if you look at that legend. And the blues are down in the low ones. If you look at the side view, where you see I sketched in a neutral axis, and you take a look, you can see the amount of blue showing up on both sides of that line. There's a lot more on the north side, less on the south. So based upon what we've talked about so far, you'd expect the top to be long, the bottom to be short. And if that's the case, it takes on the shape in the animation below. It turns into a cylinder. And this is virtually a guaranteed result with unfilled resins, unless you can promote something else in there. I think we commented on all of those. Yeah. So the symmetry is what we're after. All right. So let's take these principles and see if we can apply them. So what I did was just made up some quick models. The flat plate, we've already seen that. And then the flat plate with the two ribs. We'll take a look at that again, see how that warps. Then we'll make some changes. We'll take the same flat plate with the same ribs down below, but we'll put in a couple offsetting ribs up top. But we won't go full height. We'll just go like half height, and we'll see what that does. We'll then take the flat plate and we'll extend the same height ribs on the top side. So we have pure symmetry here, and we'll see how that comes out. And then lastly, we'll employ another little technique, which is a flat plate with those two ribs with no ribs on top, but we'll put some grooves in here. You can see it down here a little better. We'll put some grooves in here with the idea that we want to take advantage of the principle that thicker sections shrink more than thin sections. So if we can create some thin sections, maybe we can create some low shrinkage that offset the rib. Okay, so here we go. So we're just going to look at all 5 of these conditions. We're going to start with a flat plate. This is the cross section through volumetric shrinkage. It might be hard for you guys to see on your monitor, but you can see it's surrounded by blue. And the important point to make here is that blue is symmetrical. So if I drew a line through the middle of this, I'll be symmetrical all around it. So if that's the case, we might expect it to take this shape. And this is an animation of the warp, which stays very flat. Let's go to the next example, which is the flat plate with the 2 ribs. And we already saw this, but you can see through this volumetric section here view that we got a lot of blue down south, very little blue up top. This one you might expect to go into the smiley face, which is flipped around from the earlier slide, and of course it does. Now let's go to some you haven't seen. Now for these, I want you guys to think about it yourself and predict in your head which way you think it's going to go. So here's the short rib one. A couple little hints. We got a lot of blue to the south. We got more blue to the north. So we're still not symmetrical. So let's see what happens. It indeed warps the same way. But if you notice, the magnitude is less. So we did have some effect on it. We were able to drive it back down. If you go to the next image where we balanced it out, now we got the same amount of blue on all sides. It's very symmetrical. And let's see what happens. It stays very flat. So you say, well, maybe I can't put ribs up there. Enter grooves. So here we go. We got a flat plate. We got a flat plate with some grooves in it. Still the same ribs. Nothing's changed. This section view doesn't show the blue because of our scaling, but we have blue down at the bottom and we have blue at the top from those ribs, and let's see what happens. All right. So there's this lesson on what you can do with ribs and grooves and volumetric shrink to manipulate it. So now we're going to take this over into a little more different design. And this would be a clamshell.
We'd had a question about the previous slide.
Oh, yeah.
Someone had asked, why grooves and ribs?
Yeah, that's a great question. Let's get back over to that slide. Yeah, great question. A lot of times you don't have the ability to mirror over geometry on the outside. This might be a cosmetic face, for instance, and you can't put ribs onto it. But nonetheless, in order for you to get the part flat, you're going to have to introduce this balance of symmetry of volumetric shrink around that neutral axis. So one of the tricks you can do is to put in grooves, because it will thin out the walls above the grooves. And as we talked about earlier, the one principle is the thinner you get, the less shrink you get in terms of actual movement. If you can go ahead and create grooves, you can introduce some bands of volumetric shrink that'll help offset the ribs. Brian, did you want to add to that at all?
Yeah, it's like a 2-for-1, and you need to play King Solomon. For warpage, it's a great way to add on the non-cosmetic side a feature that will encourage balanced loads. And the other side is we see people put moats around features like bosses and ribs to reduce thickness for cosmetic reasons, to reduce the shrinkage in there so they don't get a dip or sink on the top surface, the cosmetic surface. But if you go too far, you can actually create a visual in that thin area where it looks like a bump or a splay almost, or discoloration. So you got to be careful about how aggressive you get.
Yeah. I've had a lot of real parts. I wish in this presentation we could show some real stuff, but NDAs don't allow us to. But we've used a combination of all these techniques to flatten some parts. And it's been quite amazing what some of these techniques can do. And sometimes you don't need a lot of movement. You can actually move the part. Longer parts are more responsive. But yeah, that's a great question. Thanks, Tom.
Sure.
All right. Back to our clamshell. So this is another shape that's not uncommon in the medical industry where you're creating a handle, 2 halves going together. I just made a really basic shape just to illustrate some concepts to you guys. On this one here, it's about a 6-inch long clamshell. We threw a little gate post here on the side. This would be like for a cashew gate. just for the demonstration purposes. So what we did, we tried some variations of this. First, let's go here. The first thing we did was take this design and make it a constant wall. Now, that's how you're taught, make everything constant. And about every clamshell design I ever see is that way, with a constant wall. The next thing we did was, let's see what happens if we play some games and we reduce the wall. So what I did was I created a same model with a nice little curve in here. It's not concentric anymore, but we start off still with the 50 thousandths wide edge, and then we taper it down to 40 at the top. So it's a 10 thousandths change in the top of the part. Now remember, from the first round of the flat plates, we tend to go longer on edges and we tend to go shorter in the middle. So this idea is to try to battle that and see what might happen if we thin it out. This one here, it's just less aggressive. So while this one reduced 10, this bottom one reduces 5, and we go from 50 down to 45 on this. So we'll take a look and see how these play out. So here's your constant wall version with a section, a volumetric shrink section here on the left. And then here is the shape that the part takes. And if you look carefully, it's not a lot on this particular shape, but it does turn into a smiley face. And the reason for that is you have that edge effect down at the bottom, a parting line, where the edges aren't shrinking as much. But yet, if you look at that red band running through it and the green at the top, you're getting a lot of shrink towards the top. So we have this asymmetrical volumetric shrink running through this part, and it's going to curl it in the way shown. So let's take the next example. So this is the 10 thousandths move. And you notice we went from a smile to a frown. Now this is where I always like to live. If I can get to this point where I can smile and frown, now I know I'm in control, and I can go ahead and make steel safe moves. So I can actually go into the tool, put this shape in, build it, run it, and then tune it into the flatness coming off of the tool for my final move. So it's steel safe, the core standing high, and we can take some off of it. So this is where you really want to get to if you can. Here's that same clamshell, but now with the 5 thousandths adjustment, and you can see there's a little less shrink going on up top or down below in contrast, but you can see here we're pretty flat. Now we've balanced out the shrink at the top of the part with the edges, and we stay really flat. And this is only a 5 thousandths move, but a lot of times does not take a lot to make this happen. But when you set up your models, you have to be able to set up your models in the beginning with these curves in them to make afterwards a little more difficult to go in your model and try to manipulate it. Brian, you got anything to add to this one, or?
Yeah, it's simple geometry. It looks like a simple shape, but yet one of the most difficult, because you're always going to be prone to warpage with this shape. You can see just from these examples. And so that little tweak in wall thickness goes a long way. And it's tough because, yeah, our design guidelines would suggest we would be better off with uniform walls. But in reality, design guidelines are like comfort food. They may taste good, but they might not be good for you. It depends on what your goals are and what you're trying to avoid or optimize for, really.
Are there concerns about structural integrity if you don't have uniform walls?
It's a great question as well. So yeah, you could be taking out material where the part's going to get hit. And when you do these things, as far as thin up, this is very slight change in thickness. You do want to validate with more simulation and do that virtual drop test to validate that these as manufactured properties are going to hold up to the virtual and the real world when it comes to product testing or product use.
Interesting.
All right. One little side note, Brian had referenced gating earlier, and we wanted to show you the impact of gating on this little shape. You skip ahead. Here we go. So here's a top view of the same part where we do the whole cashew gate into the center. But if you notice from the top here, the part warps into a little bit of a smiley face in this view. The reason for that is this is the model where we reduce 5 thousandths. So as the polymer travels over the top, it's going from thick to thin, back to thick again. So you get a little bit of a choking off of your pack phase. And so you end up with much less volumetric shrink around the gate than the opposite side. It begins to pull and create this little smiley face. So if we just move the gate to the end of the part, you'll see what happens. It stays nice and straight because now we don't have that delta from top to bottom in this view. But if you notice, if you go down to the end of the part, that other principle comes into play. We're so far away from the gate now, we're packing out less and we're getting more shrink. So if you look at it carefully, you'll see that the right end is a little narrower than the left end. So those are the kind of things you got to balance out and determine what's important to you. I guess one take-home point is you may have some gate restrictions, but you really should explore them and find out what's best for the functionality that you're after.
Yeah, the other is there's no perfect plastic part, so you really have to pick your poison or rank your risks and make that decision accordingly to what your priorities are.
Yeah. And then one little side note, never make the mistake of a clamshell of gating one way and gating the other one in another location, because then they definitely won't match up.
And you see that happen all the time.
Yeah, don't make that mistake. All right. So now what we did was, finally here, I want to show you the feature part, this laparoscopic handle. So this is a little more complex geometry. I want to show you these same concepts in play. All we did with this particular handle was focus on the handle portion of this clamshell. We focused on the handle portion and not the head being up here. We just focused on this handle. As you can see, this is a volumetric shrinkage slide looking down both directions, cavity side, core side. You'll notice on the cavity side, there's some red bands in there. Of course, that's where the ribs meet the wall. You get a lot of mass and you get a lot more shrink. So that's pulling like a rubber band, right? And then you go down to the core side, you got ribs that are happening all along here. Those ribs, as we talked about, the edge effects of those ribs, they want to go long. So everything is trying to curl this part. And that's what we want to take a look at. So the question is, based upon what we learned, what is the warp expectation of this handle? Let's take a look. So there it is. The question is, did you predict it correctly? It pretty much is going to curl just the way we thought. And this is where I'm saying, if you guys take a look at your designs, in many cases, you're going to be able to predict it before you ever shoot the part. The question is, what can we do? What techniques can we apply to fix this problem or help control it? What we did was we took the handle, and the blue surfaces here is the only area we played with. We decided we'd go ahead and apply that clamshell technique to this blue surface. So we started off, we said, okay, first let's do our baseline, which is an 80 thou wall, a uniform wall. Let's go ahead and make a pretty extreme adjustment. Let's go from 80 all the way down to 45. There's a lot of geometry here to fight. So we'll go from 80 down to 45, see what that does. That's pretty excessive. And then we tried one here, 80 at 60. Now, we didn't completely optimize this part, but I want to show you the effects of just these changes. So first off, we'll take a look at volumetric shrink. On the left is the constant one we've already looked at. In the middle is the change. We went to the 45 thou wall, and you can see all the blue that got introduced in there, and you can actually look at the shrink rates. They're quite low. Change number 2 is the 060 wall on the top, and it's went ahead and shrunk a little further again, came back a little bit more. So let's take a look at the shapes here and see how they come out. Constant wall, we've already looked at. That gives you the nice smile. We go to the 45 thou wall, which we know is excessive, at least we felt it was, and now you get it bending the exact opposite way. And finally, we go with the 60. And while it's not perfect because we haven't worked on the whole thing, but you can see that we were able to tame it down quite a bit. And with a little more time and energy put into it, we could get it better. If you take these concepts yourself, you can defeat your villain, just like we've defeated many of them. And it's not always going to be 100%, but you're going to be a whole lot better than you were before. Quick summary of what we learned. Of course, the obvious is you do not need to be a victim anymore. If you put some control into your hand, you can defeat the villain. Warp is the enemy, no doubt about it. But volumetric shrinkage is your friend. And it's nice to have a friend, and that's a good one. Use ribs to steer warp. use grooves to steer warp, use the variable wall thickness to steer warp, and then you slay your own warp villain. I'd like to end this by saying I'd like to say good luck, but I don't think you'll ever need it again.
All right, great stuff.
Yeah, so get it back to you, Tom.
Yeah, we've got a few questions here, and folks, if you have more questions, let them come. Disney did call, and they'd like you to stop using the Avengers term there. That's doesn't take long. Lawyers are everywhere. No, I'm just joking. Okay, of course I'm joking. We had a bunch of questions. Let's see if can we get up to slide 35, because we had a few people pop on. Then let me see. I'll get us over there.
Yeah, you want to get us?
Yeah. So we had. Oh yeah. Let's call up all the animations. A question from Harry. I think, and Harry, if I'm on the wrong slide, let me know. But Harry's question was, why non-uniform surface? Why not control by different mold temperature?
Oh, that's a great question.
It is.
Yeah, Brian, I think both can chime in on this one. I have fixed parts with differential mold temperature. The thing is, it's most effective with semi-crystalline resins because they got the highest shrink rate and the most movement. I fixed a part here just a short time ago. I believe it was Delrin. It had a big old disc to it and a shaft, and it was warping the wrong way. The tool was already built. This was another group. Had to go in and fix it. We did go into Moldflow. We modeled all the water lines, and we actually worked on differential temperature to tune it. And in that case, we got it flat. It worked. Now, what I found is, in my experience, is that technique works, but only for minor change. And if you got significant geometry driving your shape, most of the time you're not going to get there with just a mold temperature change. And then the last thing you got to worry about is just the thermal expansion deltas. So if your one side is hotter than the other, the bigger the tool is, the more dangerous that becomes with all your fits and shutoffs. Ryan, you got anything to add to that?
Yeah, no, that was the final point for me is you get into that point where you're sacrificing mold maintenance costs, things like flash and wearing because of the differential temperatures on the tool. And yeah, my experience has been sometimes you get lucky and that can help, but root cause is generally the material and the geometry and where you place the gates. So if you can at least improve that on that upfront side, you won't have to be tweaking the process or being to an extreme. You'll have more process window, more flexibility as far as that process window, which just makes things more cost effective.
Yeah, and I like to get as close as I can with the geometry changes. And then oftentimes it's not a perfect prediction. So you got adjustments you see out there. Maybe it's not coming out exactly like planned, but you're going to be a lot closer. And then you can use that temperature as one more tool in the toolbox to do your final.
And you never want to be on one extreme corner of a potential window or outside the limits of same material and mold temperatures.
Yeah,
it's not a good place to be as far as reliability.
Yeah.
Great.
Yeah.
All right. Next question from Brandon. What percentage of the time is the mold flow analysis prediction correct? In other words, how often does mold flow analysis indicate warp will be avoided, but the result is not validated in real life? That's a wonderfully worded question, Brandon. Thank you so much for that.
Yeah, that's a great question. I mean, yeah.
I could speak to that. It's timely because we're always improving our solvers, and we've got a new patent-pending solver for improving warp accuracy. Historically, we've been really accurate with the shape form, maybe a little off with magnitude, and we made a lot of improvements this last release in January. And most of the time when I see correlation issues, it's operator error, meaning they didn't look at the material data. It wasn't complete enough to get accuracy, or the setup didn't mimic the actual process. And that's a bulk of what I see with correlation issues. And it's a very small percent, less than 5%, where it may be solver related. And there are some pretty trick things out there where we might run into that, but predominantly we're pretty spot on. And Ray, what's been your experience?
Yeah. Just from a user standpoint, that's a great question. I say this all the time. Everything we do or make at Aptyx, we run Moldflow on, even quotes. And one of the things I found over time is that the direction or the shape factor that Brian alluded to is always right. I've never had a failure of Moldflow telling me which way it was going to bend and the part bent a different direction. If it did, there's a sticking in the mold or something else going on. So that's been, I want to say 100%, maybe somewhere back in there I've had something, but I just don't recall it at all. The magnitude side, that's a different matter. So the magnitudes aren't always dead on. So what I do is I try to come up with this sort of holy grail where if I can bend it the other way, I know I'm steel safe and I can do the final tuning when I got a piece of plastic in my hands. If I don't have a steel safe approach, then you're pretty much out of luck, short of doing something more significant or costly. I found that the direction is always really reliable and the magnitudes not always. Now, what causes magnitudes to be out? There's a lot of things. One of them for sure is the database and how well the material was tested. We always try to go to, Moldflow has a gold, silver, bronze kind of rating for their materials. So even if the particular grade we're looking at doesn't have a gold level, we'll find an alternative to run side by side at gold level and try to get a bunch of opinions out of different resins before we make any kind of decisions. But that's a great question, and it's something we deal with all the time.
It's the reality of simulation.
Yeah.
Right?
Mm-hmm. Next question from John. What about concerns where the cross-section warps inward? What about concerns with the cross-section warps inward?
Yeah. I had a recent project just that way where I was getting the part to go flat, like in this view, but when you did a cross-section, it was curving. And the reason it was curving at the time for these was I couldn't get the core geometry mirrored over 100% onto the cavity side. So I had to offset some of that, and some of that offsetting can create some warp across that middle. In those particular cases, we were able to overcome it. We used grooves, we used other techniques that we employed in there to try to help tame it down. Got it to a point that was acceptable, but it is an axis that you need to look at. Today we just showed you some simple principles, but as you get into your part, depending on the complexity, a lot of times you're going to be looking at this at a lot of different angles and directions. And the good news is if you're patient, you got this tool and you want to take your time at it, you can make significant improvements. Will you ever get a perfect part? I think we've had some, but nothing's ever going to be totally perfect. But you can be a lot better than where you're at.
And it's a journey.
Yeah.
You want to start simple and learn as much as you can when things are simple. And as things change, as you get more detail, you need to add that, repeat, rinse, repeat. And that's a best practice as far as carrying it through.
Yeah, a lot of times. Oh, sorry. Go ahead, Tom.
No, if you want to add to it, let's get to this final question, and then, folks, we'll have this final question. Oh, okay, great. Thank you. Welcome, Harry. We'll have this final question. If folks have other questions, please submit them while you're listening to the answer. If we're not able to get to them before the end of the webinar, which is likely at this point, Aptyx will certainly get back to you. You may hear from the great Ray Raydini himself. PJ is interested in getting us in trouble with DC as well as Marvel. He asks, what tools do you go to in your utility belt for fiber-filled materials?
Yeah, we know PJ. He was at our user group in San Francisco. Hi, PJ. and I just met him actually last week. Yeah, so it's a different beast. You have to follow the theory of fiber as far as radial flow will drive fibers across. And shear or diversion will line them up in the direction of flow. It's hard to visualize, and that's why you need Moldflow to show those influences of flow front shapes and gates. In some cases, placing a gate or adjusting geometry thicknesses to drive flow a certain way. Maybe you want radial, so you get a lot of cross flow and random fiber, or maybe you want to line it up in one direction, so you're only dealing with fiber in the length and cross fiber on the width. It also impacts dimension. So dimensional control is better in that length if you line all the fiber in that length. And if you have a load on that outside end to end, that's a good way to line the fiber too. So there's a lot of different part geometry as far as flow leaders and flow inhibitors, gate locations, and thickness variations.
Yeah, you got
anything else to add with that? You've dealt with a lot of glass-filled materials and successfully.
Yeah, do you got 1 minute, Tom, for me to tell a quick story? Got time?
Absolutely.
No? All right. Yeah. So
You paid for this. You paid for this microphone, Ray Raydini. You go.
Yeah, glass fiber is a beast. Your biggest defender of glass fiber is gate location. So you need to orient those strands, and that's what's going to help control your warp. But as we all know, the resin weaves its way through, and you can't get those fibers to align everywhere you want them to. I had a program here a couple of years ago. It's a pretty funny story. I'll try to make it fast. I had to mold a glass field. It was out of PPA. It was a 33% glass loaded PPA. And I had to make it's a fuel tank, pretty big one. It was an elliptical tank that had another half that made it up to it. I would say it's about 5-6 inches tall. The one axis, the canister, the one axis was probably about 5 inches long. The other one was about 3 inches long. The engineer, the customer I was working with had never had first shots come off a mold and work of these canisters because of the fiber. It just warped like crazy, and they'd have to go in and then adjust the steel, put the compensation in after first shots. So I thought about it for a while, and I thought, that's going to be me. And so why don't I just take a shot at this thing? So I actually got a hold of Brian and was running it by him. At the time, I didn't have Moldflow Insight, and I thought, I knew that Insight could go in and predict the warp shape and actually kick out an anti-warp shape. So I thought, if that's the case, if I know I'm going to be wrong, I know I'm going to be bad, I might as well take a shot at being bad and use that. So I actually used Moldflow to predict the shape, and I built the tool to it. Now, I did insert it in a way so that I didn't have to lose a lot of money changing it. And I couldn't believe my eyes. It was the first time this engineer said that he ever had a tank that went together and actually sealed right out of the gate. And the one part, the larger part, we never had to adjust. There was a cap that went to it. That one we had to do some adjustment on. And between the two, we ended up nailing it. So there's a little shout out to Insight on that. And I wouldn't have done it had I known that it would always be wrong no matter what I was going to do. So I figured, hey, I'll just go for it. But that ended up being a good lesson to me. I haven't done it since, but worked that one time through.
All right. Great stuff. All right. Well, thanks so much for the presentation. Beth, any final words from Aptyx?
No, just thank you for everyone for listening. And as you can tell from this group, they love to talk challenges, and that's Aptyx as a whole. So bring us complexity. We are here to help.
Absolutely.
Can't say it any better than that. All right. Well, thanks everybody for joining us on this episode of Device Talks Tuesday. Once again, if you're watching this on demand and you have questions, or if you're listening to this live and you have questions we didn't get to, sorry, we just got a question. We'll address that afterwards. Please submit them, and Aptyx will get back to you. So thanks everyone for joining us on Device Talks Tuesdays.